Okay, so a very short break for the online folks that are coming to the seminar. I will just provide an introduction and framework of today's seminar. This is a two series back-to-back of the visitors from Aachen University. Last week with Dr. Pooya, and now we have Dima, a PhD student at Aachen University that is working in parallel with the program that we have here at UVA in geoprint, 3D printing rods, linking links with the numerical NF. So without that, part of the loop is Dima in the technical aspect. Thank you very much.
Thank you, Gonzalo, for the nice introduction and for the opportunity to present my work. It's such a pleasure for me to be here at the University of Alberta and meet fellow students. Hello, everyone, and welcome to my presentation. So my project focuses on understanding the failure behavior and the strength of rock masses containing non-persistent discontinuities, and I do laboratory tests on 3D printed rock masses. I am supervised by Professor Florian Amann and Dr. Pooya Hamdi. Pooya Hamdi has presented here last week his work on pre-code project. So my project is funded by the German Research Foundation, DFG, and there has been a strong collaboration between us at RWTH and the University of Alberta, and specifically Geoprint facility. So that's why I'm here today, to meet the team and meet Professor Gonzalo and Angel Sanchez, who has been helping us a lot in our project. Excuse me, I can't move to this second. Okay. So as a quick preview about today's presentation, we will start by general definitions and move to project plan and motivation, and then present some results on laboratory tests and numerical modeling, and conclude the presentation and talk briefly about the future steps that we will do. So to begin with, and as it's well known here, the rock mass matrix is a combination of index rock material and discontinuities. Both have different characteristics. So, and in engineering structures, usually they deal with rock masses, which makes the estimation of the rock mass strength and failure behavior very important and crucial in engineering structures. So in real life, and as we can see on the figure to the right-hand side, a rock mass may have persistent joints. I'm just trying to get the pointer here. Okay, we can have persistent joints as shown here, and in most cases we have non-persistent joints, which are the non-persistent fractures shown here. The non-persistent joints have different characteristics. They have different orientation, different length, persistence, and spatial distribution. So this unknown spatial distribution and the limited persistence and the unknown persistence of the rock joints makes it really challenging to be able to estimate the strength of a rock mass and to study the effect of the rock bridges embedded between the rock joints on the overall strength of a rock mass. Moreover, the presence of micro cracks inside the intact material itself, and the mineralogical heterogeneity, which is inherent in the intact material, adds an extra challenge to the laboratory testing, in which we will have non-repetitive laboratory testing when we are doing our tests. We have errors in the laboratory results, and the coefficient of variation among laboratory test results on natural rocks can reach higher than 25%. So all this leads us to adopt the 3D printing technology. With this technology, we are able to print identical samples, identical rock-like samples, with known geometry and known strength properties. And this will enable us to do repetitive testing to be sure of our results, and hence decrease the coefficient of variability among tested samples down to 5% only in our laboratory test campaigns. As you are also familiar with here, the technique used in the project is called the binder jetting technique, located here at GeoPrint facility, the X1 Amflex printer or system. The process involves consecutive deposition of core material and binder material in order to form a solid at the end of the printing process. The core material that are used are silica sand combined with an activator, and the binding material used is furfuryl alcohol to bind the core materials together. The samples after printing are undergo thermal curing, and they are put in the oven at 80 degrees Celsius in order to increase the strength and the stiffness of the samples. We are using GeoPrint expertise and earlier and ongoing researches on this matter, on the 3D printing technology, in order to be able to come up with the best or most suitable printing configuration that can lead us to print a sample behaving as close as possible to the natural rocks. So, presenting the project plan in general, our main goal, as I mentioned, is to be able to understand the behavior and estimate the strength of a rock mass with non-persistent discontinuities or a discrete fracture network embedded within. So the project is generally divided into 5 working packages, starting from left to right. The first working package is done in order to is created to study the behavior and strength properties of the synthetic material. So in order to be able to say that this material behaves like natural rocks, we have to prove and we have to do experimental tests on this synthetic material, on the printed material, and to say that it behaves like natural rocks and prove it. We have performed uniaxial, triaxial, and Brazilian tests in the first work package, and studied the different and concluded the different strength properties and brittle behaviors of the synthetic material. Now, in work package 2, once work package 1 is done and we are sure that this material behaves like natural rock, we can move to work package 2, which is studying the strength of fully persistent discontinuity in this synthetic material, in the printed material. By doing so, we can calculate the friction angle, the dilation angle, and the apparent cohesion of a joint, of a synthetic joint, or a joint synthesized by this material. Moving forward to work package 3, which is the third column. The work package 3, we will increase the complexity a bit, and we will include rock bridges in our direct shear testing. So what's the goal of this? As a brief explanation, the rock bridges, as we can see here, are the intact material connecting both sides of the joints. So imagine this box is being sheared horizontally. The rock bridges are the intact material connecting the upper shear box to the lower shear box. So if we have a rock bridge percentage, as the rock bridge percentage increases, the shear strength of the rock block increases. So we can say that the joint strength increases with the increase of a rock bridge. Our goal in the third work package is to study and investigate the effect of different characteristics of rock bridges, whether it was the orientation, the percentage, or the location, spatial location of rock bridges on the overall strength of a rock bridge, or of a joint. And finally, in the last work package, after understanding the behavior of the intact material and after understanding the behavior of joints and discontinuities using the synthetic material, we are able to combine both in the last work package, which is the fourth work package, in which we will be able to print a cylindrical 3D printed rock mass, in which we will have discrete fracture network M. So we will be able to print laboratory scale rock samples with an identified discrete fracture network and non-persistent joints in, and be able to apply and directly assess the strength and the behavior of this rock mass. And with all these work packages, there will be numerical modeling going on from the first work package until the last one. We will be trying to replicate the behavior of the synthetic material, and we will be trying to replicate the tests, the laboratory tests that we are doing simultaneously. Numerical modeling will include 2D and 3D models as well. So the focus of this presentation will be on the results of the first work package, in which I will be presenting the results done on the synthetic material, the 3D printed material, and UCS, structural, and Brazilian, and see the results further. So, as I mentioned, the goal is to come up with a material which behaves as close as possible to natural rocks. In order to do so, we have set a series of requirements that if this material meets, then we can say that it behaves like natural rocks. To begin with, we examine the behavior of the material under compression. Now, how do natural rocks behave under compression? The figure on this, the illustrations here show the physical aspect of the behavior under compression of natural rocks. We have the first rock block having pre-existing microcracks or voids. When we start the application of axial load, these microcracks and voids will close, moving to this illustration. So this stage is called the crack closure stage. As we further increase the load beyond the crack closure stage, microcracks and tensile failures will start to appear in the sample. We will have additional microcracks, and we can see that the tensile failures are happening at the tips of the existing fractures. And this threshold is called the crack initiation threshold, in which we will start having failure inside the sample. As we further increase the axial load on the sample, or increase the compression, we will have the stable crack growth. So these microcracks will grow in a stable manner until reaching the crack damage threshold. So at this threshold, and after further increasing the axial load, we will no longer have crack a stable crack growth, all the cracks will coalesce and combine to form macro cracks, visible cracks at the end of the test. And after that, we will be having unstable crack growth until reaching the UCS point, the peak point at which the sample will fail. So these different stages or thresholds can be, these different stages or thresholds can be quantified or can be identified quantitatively using the stress strain curves as showed here. The figure is modified after chi, and we can see the blue curve, which represents the variation of axial stress as function of the axial strain. The green one represents the variation of the lateral strain, and the pink one represents the variation of the volumetric strain. So as we can see here, the crack initiation and crack damage thresholds can be identified using the stress strain curves. Now, for natural rocks, the natural brittle rocks, the crack initiation threshold is usually between 30% and 50% of the ultimate strength of the rock. And the crack damage threshold is usually between 70% and 90% of the ultimate strength. Now, if we are able to determine to prove that the crack initiation and the crack damage thresholds in the synthetic material are within these ranges, then we can say that our material behaves like natural rock. Moreover, the minimal requirement of the strength of the synthetic material is 25 megapascals. We said this because 25 megapascals and higher represents the strength of a moderately strong natural rock, which is acceptable for us. And further, in the strength aspect, we have two ratios, the UCS to E ratio, which is called the modulus ratio, and the strength ratio, tensile to UCS ratios. Both ratios characterizing the material should belong to the sedimentary rock domain, natural rock domain. And finally, we have the characterization of the material under triaxial compression. So natural rocks under triaxial compression have a unique behavior. The brittle natural rocks have unique behavior. Why? Because as we increase the confinement, the post-peak behavior of the samples will change from brittle behavior at low confinement into ductile post-peak behavior at high confinement. And this is a very unique property about brittle natural rocks. If we were able to prove that our synthetic material behaves like that, then we are on a good path. And finally, we should prove that the test results have minimal variability, of course, and we have to prove that the tests that we are doing are repeatable tests. Now, presenting the geometry and the printing configurations of the samples that we have printed and used in the experimental campaign. First, we have the UCS sample, the triaxial sample, and the Brazilian disc sample. Here in this work package, we distinguish two test series. What's the difference? So we have samples having a binder saturation of 14.5%. The binder saturation is the amount of binder present in the sample upon printing. So as we increase the binder saturation up to a certain point, the strength of the sample increases. So we have studied two different binder saturations characterized by two different test series. Test series A having 14.5% binder saturation, and test series B having 17% binder saturation. And the numbers here represent the number of tests done in each configuration. Now, the experimental setup. These figures show the experimental setup used at RWTH. We can see that there is a constant measurement of axial and radial strain, circumferential strain in the case of UCS, and radial strain in the case of triaxial tests by using installed extensometers and axial LVDTs. And the tests are done based on controlled displacement tests. So we control the displacement in the sample, the induced displacement in the sample, and we record the stress required to induce this displacement. Now, arriving to the results, the experimental results, the graph on the left-hand side here shows the variation of the axial stress applied as function of the strains. We have axial strain, volumetric strain, and lateral strains. And we have represented both test series A, which is represented by dashed curves, and test series B, which is represented by continuous curves. And we can see that test series B, having higher binder saturation, achieved higher UCS value, 32 megapascals, compared to the test series A, which is around 27 megapascals. And the behavior of the sample is obvious in the case of test series B, in which we can see the initial, as we start applying the load, we can see this nonlinear behavior here, which is the crack closure behavior, until reaching a crack initiation threshold. The crack initiation threshold is identified using the lateral strain. It's not pinpointed here, but we can still see the linear variation and the linear relationship between the axial stress and strain in the axial strain curve, the red one, in which we have a stable crack growth in the sample. And then we reach this point in which we have the deviation from the linearity in the axial and the strain curve. And this indicates the crack damage threshold, in which the damage in the sample starts to go out of control or increase in a non-stable manner until reaching the peak stress, which is the UCS. And after that, we have a brittle behavior, a sudden stress drop in the samples. This is the typical brittle behavior, as we can see, and it's a good sign of for us to move forward. Now, from this graph, we have extracted the crack initiation and crack damage thresholds to see if they belong to the natural brittle rocks domain. And yes, they do belong. So this graph shows the crack initiation and crack damage thresholds of test series A and test series B, these points. And we can see that the crack damage threshold is at 75%, which belongs to the natural rocks. And the crack initiation is around 35%, which also belong to natural rocks domain. And these other points are the crack initiation and damage thresholds to other natural sedimentary rocks. Now, on this slide, on the right-hand side, we can see we have plotted the strength ratio and the modulus ratio. The strength ratio, first of all, is the tensile strength over the UCS. And this graph here shows the distribution of natural sandstone data points and their strength ratios. So the plotted data points here for test series A and test series B can be directly compared to the natural data points. And we can see that the strength ratio of the series A and B belongs to the higher domain of the natural sandstones. And belongs to the higher domain. And for the modulus ratio, which is UCS over E here, I have plotted the domains of natural limestone, shale, and sandstone, and we can see that the data points from our test results and the behavior of the modulus ratio in our material belong to the lower range of the natural rocks, which is here. This behavior is seen because of the high porosity present in the samples. So the high porous media in our samples, the high porosity which can reach 35 to 40% of the sample, decreases the stiffness, enhances the strength in the samples, and leads to low elastic modulus, low Young's modulus, low E, and low UCS compared to tensile strength. So this is why we have seen this behavior, but they are still in the acceptable domain, and we can move forward in our project. And now these laboratory test results are of the samples undergoing triaxial compression. We can see here, so this graph represents on the x-axis, the confinement pressure applied to the samples. And on the y-axis, the failure stress, or the stress at which the samples failed on each particular confinement. So the green ones belong to test series B, and the orange ones belong to test series A. And this blue dashed line here is the Mogi line. The Mogi line separates between the brittle and ductile post-peak behaviors in the sample. So all the data points on the left of the Mogi line, we know that they have failed in the triaxial conditions in a brittle manner. So the post-peak failure, post-failure behavior was brittle, and all the data points on the right side of the Mogi line had a post-failure behavior which is ductile. And the curves, failure curves, Moore Coulomb failure curve, the linear one, and the Hook-Brown failure curve are fitted on these data points for both test series, and they are fitted only on the points to the left of the Mogi line as recommended, which are the points that failed in brittle manner, points representing the samples that failed in brittle manner. And from these curves, we have extracted the MI, Hook-Brown constant, the cohesion, and the friction angle. And despite that, the UCS and other strength properties are acceptable, we can see that the friction angle is relatively low compared to natural rocks, which is usually between 25 and 30 degrees. We have it between 15 and 16 degrees. This is as well due to the high porosity and the low slope here, the low slope fitted on the points. So to explain this, as we increase the confinement, the samples undergo axial compression, and this will favor the line to go towards the Mogi line. So we will reach the strength threshold higher than more quickly than in natural rocks, which decreases the slope of the Moore Coulomb and hence decreases the friction angle and result in 15 to 16 degrees of friction angle. These figures here show the transition from brittle failure to ductile failure of the samples, of the 3D printed samples. When increasing the confinement, we can see that there's axial splitting at zero confinement pressure or UCS, and then the shear behavior starts to appear in the samples as we increase the confinement up to 5 megapascals. We can see a clear shear band in the samples occurring. And when we further increase the confinement to 15 megapascals, we can see a pure ductile behavior with no visible fractures. Now, returning to this, the low friction angle at higher confinement, the low friction angle and the non-resembling behavior of the samples at higher confinement is not in our concern, and we can overlook this problem because we will be dealing with samples undergoing low confinements in our future projects. So this will not be a problem for us, the behavior under high confinement. Now moving to the numerical modeling, after having the set of data that allows us to do the numerical calibration on models, we can move to the numerical modeling. The approach that I've used is the combined finite discrete element method, which I will explain later on. Now, what's the combined finite discrete element method, the FDEM approach? It's initially developed by Munjiza in 1995, and it combines the continuum and discontinuum elements in a unified framework. So the simulation starts by a continuum entity or a set of continuum entities, and as it progresses, these entities undergo elastic deformation, translation, rotation, and can fracture and form new separate discrete entities. So we can be able to see the clear transition from a continuum media to discontinuum media. What are the advantages of the FDEM or finite discrete element method? Firstly, it allows the simulation of the fracturing process and brittle rocks, which is the fracture initiation, propagation, and coalescence. It secondly allows the accurate representation of the stress distribution or the stress field around the fracture on the fracture zones. And moreover, it allows the explicit implementation of the discrete fracture network inside the samples, which is also a very good advantage. And finally, it allows us to model complex geometries regardless of the complexity of the geometries. So how does the transition from continuum to discontinuum happen in this approach? And what are the main principles? In real life, we can see this GIF. It represents the transition from continuum to discontinuum media. We can see that the fracture that's happening is explicitly. So the FDEM can replicate this behavior. In the numerical modeling, first, if we start by the intact domain, the intact domain is discretized into finite elements, triangular finite elements shown here. And these elements deform elastically and have a linear elastic deformation. And the fracturing process happens in these zones, or is represented by the blue zones. The blue zones are called the crack elements. They are 4-noded elements implemented between the triangular finite elements, and they represent the potential fracture that will happen in the material. So these blue elements, when we apply the forces on them, and when we have a displacement in the wall of the fracture, they will yield, they will start to fail. We can see here the yielding in the orange. They will yield, and then they will break, they will disappear. And this breakage represents the actual fracture in the material. So we can see the clear transition from a continuum media here. These are, the crack elements are here, but this is an exaggerated view of them. The yielding of the crack elements, and hence the disappearance of the crack element, which is the fracturing happening. This figure here also shows the material itself, the intact continuum material, the yielding part, where micro cracks and the potential failure is happening, and finally the splitting of and the fracture happening. Now, after the fracture happens, we will have two separate discrete bodies. For example, these two elements. These two elements will react as well, and there is a specific detection algorithm which detects if the two discrete bodies are in contact, and hence create the reactional forces applied between these created between these bodies. Now, what are the models, geometry, and input material used in the numerical modeling? These geometries represent the 2D numerical models that I've used in order to replicate the UCS and Brazilian discs and triaxial tests of the 3D printed analogs. They represent the mesh, the discretized mesh, the boundary conditions, and the dimensions. And the test results, which are the results that are concluded from the experimental testing, are used as the first input parameters and used to calibrate these models, further calibrate. So these are the sets of the final input parameters that I've used in the model, and that resulted in a representative failure behavior and strength of the rock analogs. We can see that the first set is the strength properties that define the elastic behavior, which are the elemental properties. The second one is the strength parameters, which represent the strength of the intact material itself. And the third set of properties governs the behavior of the fracturing and the interaction of discrete bodies. Now, for the purpose of comparison, I have put the laboratory test results and the failure mode happened in these laboratory test results. We can see in the Brazilian disc, the uniaxial, it's a combination of shear failure and tensile failure. And in triaxial tests, we can see a clear shear band at high confining. And these GIFs here represent the numerical models that I've obtained using Erazo. The software that I'm using is Erazo, and it's provided by J Mechanica company, also here in Toronto. I forgot to mention that. So we can see quite a good resemblance between the numerical models and the experimental results. Now, if we plot the strength and the more Coulomb envelope on this strength, we can see that the green one is the numerical results envelope, and the red one is the experimental results envelope. We can see that the tensile strength is relatively low compared to the experimental result. We had around 4 megapascals of tensile strength in the model compared to 5.5. And this might need further calibration. We know why is this happening, and in the compression side of the curve, the positive confinement, we can see a good coherence between the experimental results and numerical results. We have a good coherence of the friction angle and the cohesion as well. So to conclude the work, within this work package that I've been working on, we were able to prove that the synthetic material can behave as natural brittle rocks and can be used as a rock analog, specifically sandstone analog. The relatively low friction angle and Young's modulus values are inevitable, as I mentioned, due to the high porosity present in the samples, which is between 35 and 40%, compared to natural rocks that have a porosity around 15%, 10 to 15%. And we have concluded as well that the finite discrete element numerical models were resulted in a good replication of the tests and of the behavior of the rocks, of the rock analogs. And there was a discrepancy in the tensile in the Brazilian test due to the high BTS to ECS ratio. I can explain that later if needed. And if needed as well, and the further work packages, we can do further calibration to calibrate more the Brazilian test. So these results are considered to be promising in order to move further in our work and continue to work package 2, which will be at first the direct shear testing. So the next step of our project will be characterizing the behavior of a rock analog joints, as I've mentioned, under direct shear testing. And we will be able to study the effect of different rock bridges here, the different number of rock bridges, different percentage and location on the overall strength of the rock joint. This is only possible using the 3D printed technology, as we will be able to print these geometries and do repeatable tests on them. And on the right-hand side, we can see the ultimate goal of our project. So the ultimate goal is to be able to print a 3D cylindrical samples with discrete fracture network in them, as you can see, of different persistence and orientation, and be able to do direct testing, direct uniaxial and triaxial testing on these samples, and directly assess their strength and failure behavior, and to try to replicate and model these samples using the FDEM approach. And this, as far as we know, the first attempt to use directly do direct experimentations on UCS samples on laboratory scale rock masses, and assess their strength and failure behavior away from empirical relations, and be able to calibrate the models on experimental results that are directly provided by the laboratory test results. So by this, I will be ending my presentation. And these are the set of references that I've used earlier. And I'm happy to answer any question that you have. Thank you. Yeah.
So on page 9, shows a picture of
Mm-hmm.
So yeah, here. So the vision direction
Mm-hmm.
that is parallel to the building.
Yeah. Yeah. So actually, we have tested several printing directions, several options. We have tested parallel to the loading and perpendicular to the loading. And in the case of Brazilian test, we have also tested the case of printing direction in this case. And we have studied the effect of the printing direction on the overall strength of the Brazilian disc. We have found that the printing direction does not affect the overstrength, does not significantly affect the strength of the Brazilian disk, but I haven't showed these results in this presentation because they are not yet concluded correctly. Mm-hmm.
Yeah, so on the bottom, are these the pictures that you were just extracted from the interior image of the 3D block?
No, these are the experimental rocks.
So these are the experimental.
Yeah, these are representation of the failure that we have seen after the experimental results.
Like the data, I think in this graph, 90% more than 90%.
Ah, these ones. Yeah. They are, sorry, from the numerical model, and you can see here this shear and tensile failure and tensile these data are provided by the model. Yeah, I'm sorry, this is my fault. No, I should have put the lab results here, but you can see the lab results here.
Yeah.
You can see that there is a combination of axial and tensile splitting, and finally we have a shear failure, which was the case in our numerical models. This shear failure.
So how the impact model that model?
Mm-hmm.
Did you include the porosity of the model or
No, the porosity is not included, explicitly included is just a solid rock. So the porosity in real life affects the strength and the elasticity of the sample, which are directly implemented in the input parameters of the rock, affecting the strength parameters and elastic parameters. No, please. Yeah. Thank you. It's good to hear that. No, we haven't reached the creep behavior in our experimental tests and triaxial tests because the duration of the test was around 30 minutes overall. So we have applied in few minutes the isostatic confinement, and after keeping this isostatic confinement constant, we started applying the action load, and the samples directly failed. Wow. No, but it would be interesting to look into that aspect. Yeah. Okay. Yeah. Yes, thank you for the idea. Yeah, it's valuable to see the creep behavior of the 3D printed samples. Okay.
I think you have a question.
Okay. Any other questions? Yeah.
Very interesting. I know that you're going to scan your restricted samples, see the scans. But for the ones that you already printed, have you ever tried scanning them with the scanner or the
No, Because firstly, the scanning is already done in previous researches in which we are able to see closely the structure of the 3D printed samples. But at the first of in the project proposal, there was a CT scan done on such type of rocks, in which we have printed a non-persistent joint inside the rock, and we printed this configuration, and we took this rock into the CT scan, and we have seen the actual non-persistent joint inside the rock, which was a promising result for us. It shows us that we are able to print discrete fractal network inside a laboratory scale rock mass. Yeah. Thank you.
Two comments. More than
The experiment, yeah. Okay. It's actually the closure of the voids existing, not the cracks, not the micro cracks, because there are no visible, there are no explicitly printed micro cracks in the rock. So the closure that happens is due to the closure of the voids upon applying the compression. Exactly. Pore collapse, and that's why we have seen this and the triaxial test. So as we increase the confinement, we have pore collapsing, and we have axial compression dominating the behavior, which results in the low friction angles in the from the fitted curves. This one. Yeah. 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 This is the actual Poisson ratio of the 3D printed material. Because again, because of the compression, because of the dominating axial compression happening in the samples, there is no radial expansion happening even close to the failure. We don't have radial expansion. We only have axial compaction because we have collapsing of the voids. And this results in a very low Poisson ratio, because the Poisson ratio is the ratio between, the applied axial stress to the dilation. So we have very low dilation happening in the samples because of the high porosity found in the samples. Yeah.
Very good presentation. Thank you. Just one quick question. At some point you mentioned the transparency. I think
Sure. Yeah. So what you can see here in the Brazilian disc, you can see the failure starting from this point. Yeah, it will be shown afterwards. And the failure starting in this point is not the typical Brazilian failure. Brazilian failure should start from the middle of the disc, and propagates toward the two edges. Here it starts from this side and propagates. And this happens because failure happens in shearing manner. So it's not a tensile failure. The tension is happening here. It doesn't fail, but due to the compression of the platens, failure happens in this region because the strength properties of the intake material are low, because we have low Young's modulus and low UCS compared to the high tensile strength. So the specimen fails in compression rather than tension, and this results in a very low tensile strength. If you look closely into the stress at the middle of the sample, we can see that it reaches up to 6 megapascals, which is the correct tensile strength. But we are not able to see that because we are experiencing failure in compression, which is decreasing the strength of the sample, and we are not reaching the tensile threshold before that. Now, we can further calibrate the models if we need to move forward in the work packages, but this is not our priority yet. Mm-hmm. Mm-hmm. Yeah, yeah. It's the behavior of the material. Yeah.
Allow us to categorize it's and get the same possible values that we see, but we couldn't go any other way. This is a framework that we can use. This is a model that allow us to test numerical tools and allow us to now look at heterogeneity and many other elements that we're going to see in that materials. You know, that's the big game change now that allow us to feed samples and feedback numerical models, see the reaction. That's another thing. That's how we see the discussion. You know, so that some of the nonsense about how close they are to natural materials, but there are some gaps. But the advantage that we can repeat the same values, same properties, and that we couldn't do any other way. So that's the whole for them.
Exactly.
With that, I think it's thank you, Dima. Thank you for your presentation. It was fantastic, and there's more to come.
Yes, definitely. Thank you. Thank you for having me here.